This section starts on page 81, so you got your book open still. You might as well just flip a page and get there. It's on diffusion and osmosis. Our objectives are going to be to talk about passive transport and describing that. Also, to go with that, we're going to talk about active transport, but we'll get to that in the next section, I believe. And then we're going to distinguish between osmosis, diffusion, facilitated transport, all of which can be passive depending on the context. I just talked to you guys not too long ago about how some things can go through the membrane directly, and they'll do so automatically. Okay? Some things need a little bit of help, like the water, to go through the channel protein. But at the end of the day, none of those transports that we talked about on this slide require energy. It just happens automatically. So they're all forms of diffusion. They're all passive transport. So where are we? Way over here. Okay, so we need to know what passive transport is. It's movement of molecules that does not require energy. I'll show you guys a demo. Chris is going to miss out on this, but I can show it to him more easily some other time.
What is that?
I got water here, just water. But there's molecules in this water, and those molecules are always moving. You guys know that. Even if you can't see them directly, I mean, you see water when it's moving. If it's boiling, when they have lots of energy, you can definitely tell that they're moving. But when it's cold water, you might not necessarily notice that they're moving, but they are. Right? Even the particles in this desk, it's a solid, but they're still moving. They're vibrating around fixed positions, but the only time particles stop is when that temperature reaches absolute zero, and that doesn't really even exist. It's just theorized. So particles are always in motion. And if you got a cell that's full of water, right, those particles are moving. It's not solid, so they're not just stuck in fixed positions, still vibrating. They're definitely allowed to move and flow, and everything is moving and flowing around in there, even if you don't notice it. So we're going to talk about movement of molecules that doesn't require energy. We're going to talk about concentration gradients. A difference in concentration from one area to the next. So I'm going to put some food coloring in this water. So I'm going to put a drop of this yellow. I'm going to put a drop of blue. And you can see right now where that dye is really concentrated, because it's all just in one little location, but eventually that dye is going to spread out and you're going to have an equal concentration throughout the whole solution. So we have a concentration gradient that you can see right now. There's yellow, there's blue, and then there's just clear, because the yellow and blue hasn't gotten there yet. So there are different concentrations in that solution we're looking at. So there should be some kind of diffusion, ultimately. Molecules always tend to move from areas of high concentration to areas of low concentration. Another demo that I could think about doing, but you guys would probably all get injured in the process, and if I shoved you all in this corner over here and told you to start moving randomly, just start moving in one direction or another, and if you run into something, turn around and move the other way, eventually you guys would all spread out throughout the room. Like I said, I can't really do that because you'd all end up injured or mad or whatever. But the basic idea is pretty easy to follow. If you're all stuck in one place and you start moving, you have to spread out. It's impossible for you to all stay in that same place. So the same thing in here. You have areas of high concentration and low concentration, and things are going to start to move to equilibrium. Right? They're trying to spread out, those molecules are. So I'm not even gonna touch this throughout class today, but eventually, yellow and blue make what?
Green.
So you're gonna see that the entire solution is not gonna look blue and yellow, it's gonna look green, and it's gonna happen automatically, because particles are moving. Even if they're moving slowly, they're still moving. I could make this happen faster, but what would I have to do?
Heat it up.
I'd have to shake it, stir it,
Boil it.
I could heat it up,
Or
but
if you
all of
freeze
those things require energy.
it,
It would take slower if you cool it down.
And we're talking about passive transport. That doesn't require energy. So I'm just gonna leave it alone. It should do it anyway. It should move and mix anyway without any extra energy. It might happen a lot faster if I put energy into it, but it doesn't require energy. That's what diffusion is.
It's all thinking.
So you're always gonna have things moving down or with their concentration gradient. When I say that, sometimes you just like, what does that mean? Right? When I'm saying with its concentration gradient, or if I say down the concentration gradient, I'm just saying that things always move from areas of high concentration to areas of low concentration. So it's going to move from where the blue is now to where it's not, which is the rest of the water, until you can't even tell there's blue anymore. It's all just green because it mixes with the yellow. And it happens automatically. It doesn't require any energy, and that's important. If it costs you energy to get oxygen inside of your cells, that'd be a problem. You needed the oxygen to get energy. So without energy, how are you going to get oxygen in your cells? It wouldn't happen. But it works because the concentration of oxygen in your blood is supposed to be a lot higher than the concentration of oxygen in the cell. Because you're constantly using that oxygen in the cell, and it's turning into water in that respiration process. Whereas you're breathing as we speak, hopefully, and you're replacing that oxygen in your blood, and there's a constant amount of oxygen in your blood so that you can get that into your cells. And this transport is simple diffusion. It doesn't require energy. It happens on its own. If it cost you energy, it wouldn't be worth doing. You wouldn't have the energy to make it happen because you need the oxygen for that. Carbon dioxide. There's a buildup of that in your cells because you produce it in respiration. It's toxic. You need to get rid of it. But again, as long as Jake's still breathing, that carbon dioxide concentration in his blood should be relatively low compared to that of the cell, because once that blood gets to the lungs, the carbon dioxide leaves the blood, goes into the air that you're breathing out right now. So that needs to happen automatically, and it does. Now, if Jake stops breathing, then this concentration starts getting bigger and bigger. And then, are you still going to have carbon dioxide exiting your cells? Not as quickly, and maybe not at all. And then you're going to have issues. Also, if Jake stops breathing, I'm probably not going to have a constant amount of oxygen in my blood. That's going to continue to drop until you have nothing left for your cells to use. So you'd have some problems, some issues. But things always move from high to low. So these next two questions, they're really kind of demo. Well, I'm going to put drawings up here, and we're going to go through the questions together. You still got a whiteboard out, right?
Yeah.
We're going to use that. So I have two solutions separated by a semi-permeable membrane.
Is this going to be in our paper or no?
Yeah, put the picture just like I'm putting it. You're not going to answer this with words. You're going to draw. Hopefully you understand the drawing. I have solution A, and I have solution B, separated by a semi-permeable membrane. It says solution A has a higher concentration of salt than solution B. So salt is made of sodium and chloride ions. So I have lots of ions floating around on this side because it's got a high concentration. Doesn't really matter how I put these in. I'm just trying to kind of do it randomly. So lots of little ions floating around. It's very concentrated. Whereas solution B has a very low concentration. There's one sodium ion and there's one chloride ion. That's it. So I told you that things just move randomly. It's not like they actually choose where they're going, they just kind of move in random directions and they tend to move away from each other, ultimately. But this sodium ion here could move across the membrane from B to A, and this sodium ion here could move across that semipermeable membrane from A to B. But there's a tendency in this scenario for it to move more often in one direction than the other. I told you things always go from high concentration to low concentration. So on your whiteboard real quick, don't blurt out an answer. You're either writing left or right. Which direction net, even though sodium can move this way and that way, overall, which way is it going to move more if I just let this solution work its way to equilibrium? So it's just left or right. What direction does the salt want to move?
I know. I was just thinking directions now. Let's go.
Okay, so I have a lot of answers, and overwhelmingly, you're telling me that it's moving in this direction net.
Here it is.
But it's not.
Which means that more sodium ions are going to make their way this way and then are going to make their way back. Remember, it is random motion, so technically some will move to the left, but more will make their way to the right than to the left. So overall, that's my answer, that red arrow. It's going to move to the right. So if you need to write that out somewhere else, if you drew all the other arrows, then you're going to be confused. But generally speaking, solute always wants to move from high concentration to low concentration. But that red arrow is for the solute and wants to move to the right towards solution B. Okay, everybody good with that? Now we got the next question. We have the same solution, two solutions, but one slightly different factor. I still have a high concentration of sodium chloride in solution A and a low concentration in solution B, but this time we're assuming that sodium chloride, the sodium ions, chloride ions, can't move across the membrane. Because maybe there's no channel proteins for them to go through, whatever, doesn't matter. But if this salt can't move, but the solvent can, the water can, you also have to know which direction it's going to want to move. So things always move from high concentration to low concentration. But you have to think about for a second, and this is going to be another whiteboard thing just to make sure that we all kind of get this and we're all on the same page. If I have a high concentration of salt over here and I have a low concentration of salt over there, which solution has a higher concentration of water relative to the salt? They probably have the same amount of water. It's the same volume on both sides. It doesn't matter. But which side has a higher concentration of water relative to the salt? So this time you're writing A or B, or you could probably still do left or right. So which side has the higher concentration of water relative to the salt? This one I would guess that maybe we might have a few more wrong answers, but that's okay. Which side has a higher concentration of water relative to the salt? So it's still left or right or A or B, it doesn't really matter how you answer that.
Scared me.
Behind your head, I could see it. What was it?
Zero goes.
Okay, actually most of us still doing a pretty good job. If this is a low concentration of salt, that means relative to the salt, I have a fairly high concentration of water. And this would be relatively low. compared to the salt. So now again, on your whiteboard, it's either left or right. Which direction does the water want to move? If the salt can't move and the water is going to move instead, which direction is that water going to move? The left or right answer. Remember, water is actually going to move in both directions, but more of it's going to move one way than the other because it always wants to move the way everything always wants to diffuse. Okay, we're doing a good job. We are so smart. I told you that stuff wasn't hard. You just have to make sure you keep up step by step. The solute wants to go this way. But if it can't move, and instead the water has to move to make this kind of even out, the water is going to have a net movement to the left because that's where the low concentration of water is. So when we have this beaker here still with the colors that are mixing right now,
It's green.
not only is the yellow and the blue starting to move to areas of low concentration, but you also have water from the low concentration areas that's moving in between those particles and helping pushing them apart. Everything's happening at once. All the molecules are moving. But water tends to move towards high concentration of solute. And we usually refer to the concentration of the solute, not the water. So you have to think about that relative. If it's high concentration of solute, that actually would mean a low concentration of solvent relative to the other thing. So that's when we start talking about osmosis.
Diffusion of water.
It is the diffusion of water. So fill in your blank, whatever needs to be filled in. And on this one, you guys might want to make a correction because I screwed up. This was not supposed to say low to high. It was supposed to say high to low. So you might want to fix that. My brain was tricking me because I was still trying to think about going towards high concentration of solute. So although the water does want to move from high concentration to low concentration from its own perspective, it still does move towards the high concentration of the solute, and that's what we usually talk about, is the concentration of the solute, not the water. So you have to think backwards a little bit when you're doing that. Now before you flip it to the other side too, there's a certain amount of pressure associated with osmosis. If I had a tube that had kind of a U-bend to it, and I put water in there, the water level would be the same on both sides, right? Gravity would make it be the same on both sides. But if I put a semi-permeable membrane down here, and I make it so that there's a low concentration of salt on one side versus a high concentration of salt on the other side, and that salt can't go through that membrane, but the water can move. This is osmosis again. So, one more time. If I put low over here and high over here, concentration of salt, which direction does the water want to move?
Low. No, low to high first.
Okay, I just want you to write it on your whiteboard. Left or right. Which direction is the water going to want to move here?
Oh, in there?
Yeah, the salt can't move. I didn't put the concentrations of the water in there, but you can infer what they would be. Which direction does the water want to move? To the left or to the right? We've got different answers. We'll talk about it.
Oh,
Yeah, because there's a higher concentration of salt on that side.
Doesn't mean it's right, but you're the different answers.
Mr. Morris, am I right?
Right.
You always have different answers.
What?
I knew which one.
What were you doing? so somebody's gonna be able to give me the right answer. And even if not, we'll figure out the right answer, because if you're wrong, then the other answer's right. But which direction do you think the water wants to move, Jared?
Right.
And you would be correct.
Because there's a more concentration, so there's a.
The water's gonna
Concentration
move
of
towards
salt.
the high concentration of the salt because that's where the low concentration of the water is. But if the water moves to the right, what does that do to this water level?
Goes up.
Look what I just did.
And that's working against gravity, correct?
Whoa.
So and that actually will happen if you set up something like this because there's a certain amount of pressure that osmosis can put on this situation. Whatever pressure, whatever force you'd have to use to push this side down and make it balanced again, that's equal to the osmotic pressure. And if you think about that in context of a cell of that little water balloon, what happens when that pressure builds up too much? It pops, and your cells literally can pop if they're in the wrong conditions. Because if there's a big pressure into the cell,
Is that harsh?
your membranes you wouldn't feel it necessarily, but if somebody gave you the wrong kind of IV solution, it would kill you ultimately because all of your blood cells would pop.
I've got a question for you,
It's
Mr.
not okay.
I've got a question for the teacher.
Yeah.
Okay, so osmosis, what's it supposed to do to water? Purify it or what?
Oh, when they do the filtration by osmosis?
Yeah. Like Gush does it, but